What if I told you that the cloud isn't in the sky, that every message, every video, every voice you've ever sent travels through threads of glass deep beneath the ocean? This is the hidden internet, and it will change how you see the world. When you send a message from New York to Tokyo, most people imagine your data flying through the air, bouncing off satellites high above the Earth. But that picture is almost completely wrong. Satellites carry less than 5% of the world's data. The rest travels somewhere far stranger. More than 95% of all international internet traffic crosses the sea, not the sky. Right now, beneath thousands of meters of water, pulses of laser light are racing through glass fibers thinner than a human hair. This is the real internet. But why? Why use cables under the ocean when satellites circle the Earth right now? The answer is simple. Satellites are slow, expensive, and can't carry much data. A single modern undersea cable carries over 200 terabits per second, enough to stream tens of millions of HD movies at the same time. Satellites carry just a tiny fraction of that. And while satellite signals take half a second to bounce back from space, light in a cable crosses the entire Atlantic in just 60 milliseconds. For the modern internet, cables aren't just better, they are the only way. Today, more than 600 submarine cables stretch across our oceans. Their combined length is over 1.5 million kilometers, enough to wrap around the Earth 35 times. The shortest is just 131 kilometers between Ireland and the United Kingdom. The longest, called To Africa, stretches 45,000 kilometers, connecting 33 countries. But this didn't happen overnight. The story began in 1858, over 160 years ago. The first transatlantic cable was laid by ship between Newfoundland in Canada and Valentia Island in Ireland. It carried Morse code, dots and dashes of electricity through copper wire. Queen Victoria sent the first official message to the American president, a miracle for its time. But the cable was fragile. Engineers cranked up the voltage to send signals faster and burned the cable out in less than a month. 2 more attempts failed. Finally, in 1866, a stronger cable held. The age of global communication had begun. For the next century, cables carried telegrams, then phone calls, all through copper wires. Then in 1988, everything changed. The first transatlantic fiber optic cable, called TAT8, replaced electricity with light. Capacity multiplied 1,000 times overnight. This single invention, switching from electrons to photons, created the modern internet we use today. But how does light travel through glass for thousands of kilometers without leaking out? The answer is a beautiful piece of physics called total internal reflection. Inside the cable is a glass core, a thread just 9 micrometers wide, 10 times thinner than a human hair. Around it is a second layer of glass called cladding, with a slightly different density. A laser at one end flashes on and off, billions of times per second. When light enters the core at a shallow angle, it hits the boundary between core and cladding, and instead of escaping, it bounces back. And again, and again. The light zigzags down the fiber at 200,000 kilometers per second. Every flash of light is a 1, every gap is a 0. That is how your data is encoded. But here is something even more clever. Engineers don't send just one beam of light through the fiber. They send dozens, each in a slightly different color of infrared light. It's like sending many separate conversations down the same pipe, each one painted a different color, so they don't get mixed up. This trick multiplies the cable's capacity by 100 times. Now you can't just drop bare glass into the ocean, so engineers wrap the fragile fibers in layers of armor. At the center, the optical fibers, the heart of the cable. Around them, a waterproof gel that absorbs mechanical stress. Then a copper tube carrying up to 10,000 volts of electricity. Then strands of high-strength steel wire for tensile strength. Then insulation. Then a tough polyethylene outer jacket. And the whole cable is still only as thick as a garden hose. Light gets weaker the further it travels through glass. Without help, the signal would die long before crossing an ocean. So roughly every 80 kilometers, engineers place a device called a repeater. Inside each repeater is a section of fiber doped with the rare earth element erbium. A pump laser energizes the erbium atoms, which then boost the passing signal without ever converting it back to electricity. These repeaters sit in the dark under crushing pressure, designed to last 25 years without maintenance. Where the cable meets land, it arrives at a cable landing station, a heavily secured building near the coast. Let's step inside. You'll find rows of humming servers, optical line terminals, and racks of monitoring equipment. Here, the optical signal is converted back into electrical signals, decoded, and routed onto the national backbone. From this single coastal building, fiber cables radiate inland to the capital, to data centers, to every major city in the country. Your message, just landed from the seabed, now flashes inland at the speed of light. These stations are critical choke points. Damaging one can cut a country's internet capacity by half. Laying a cable across an ocean is one of the hardest engineering jobs on Earth, and it begins, long before any cable touches the water, with the survey. Specialized survey ships spend months mapping the seabed with sonar, scanning the ocean floor meter by meter. Multi-beam sensors paint a three-dimensional picture of the seafloor, while sub-bottom profilers see down into the sediment itself. Engineers hunt for earthquake zones, underwater mountains, unstable slopes, old shipwrecks, and busy fishing areas, and design a route around all of them. Only once the perfect path has been confirmed do the cable-laying ships move in. One ship can carry 9,000 kilometers of cable, coiled into massive tanks. It sails the route at about 10 kilometers per hour, unspooling cable behind it. In shallow water, a sea plow buries the cable up to 3 meters deep, to protect it from anchors and fishing nets. From planning to live service, the entire project takes 2 to 4 years. Now let's follow your message. You press send in New York. Your phone passes the data to your home Wi-Fi router. The router sends it through neighborhood fiber to your internet provider. From there, it travels along terrestrial fiber to the cable landing station, where it is converted into pulses of laser light and launched into the undersea cable. The light crosses the Atlantic in just 60 milliseconds. It races past Europe, through the Mediterranean Sea, down through the Suez Canal in Egypt. It enters the Indian Ocean, sweeps past Mumbai, lights up the choke point at Singapore, turns north along the South China Sea, and finally surfaces at a landing station near Tokyo. Total distance, 20,000 kilometers. Total time, less than 1 second. Despite all that engineering, cables break. Somewhere in the world, a cable fault happens roughly 3 times a week, more than 150 times a year. 70% of breaks are caused by humans, ship anchors, and fishing trawlers. 12% are natural underwater landslides and earthquakes. A repair ship races to the location, drops a grappling hook to the seabed, drags it until it snags the cable, and lifts the damaged section to the surface. A specialist technician fusion splices each tiny fiber back together by hand. A single repair can take up to 24 hours. Submarine cables are physically vulnerable and politically critical. A handful of narrow sea routes, the Red Sea, the Strait of Malacca, the Egypt corridor, carry a disproportionate share of the world's internet traffic. A coordinated attack on these choke points could disrupt the global internet for weeks. Cables are now a central piece of modern geopolitics. Navies and surveillance systems quietly guard them around the clock. For most of history, cables were owned by consortiums of national phone companies. But today the biggest investors are the tech giants. Google owns cables like Curie, Equiano, and Grace Hopper. Meta leads to Africa. Microsoft is a partner on Maria. Amazon is building its own. The companies that run your search engine, your video calls, your shopping cart now also own the pipes your data flows through. And the network keeps growing. New cables push capacity beyond 500 terabits per second. A new technology, space division multiplexing, could multiply that 10 times again. AI systems now monitor cables in real time. And some cables have become scientific instruments. The tiniest vibrations in the glass can detect earthquakes and even warn of tsunamis. Right now, as you watch this, billions of conversations are flowing beneath the oceans. Emails, calls, bank transfers, videos of strangers and videos of loved ones. All of it light bouncing through glass, drifting through the silent deep. We call it the cloud, but the cloud isn't in the sky. The cloud is at the bottom of the ocean. And now, you know, if this opened your eyes, hit subscribe. The world has plenty more secrets to show you.